We are now going to start chapter 7, oceans, and we are going to talk about today 7.1, just kind of give you some introductory information all about oceans. Now, where we live, it's kind of a weird thing to think because we don't live by oceans. When a lot of these things, if you live in a climate or you live somewhere close to the ocean, maybe secondhand knowledge, for us living in northern Minnesota, definitely not secondhand knowledge to us. So 7.1, Introduction to Oceans. They are so important really when you think about it, even when you think about how much of Earth is covered with oceans. So ocean water, if you've ever been in ocean water before, is salty. So when you get it in your mouth, it's like, it does not taste very good. Open your eyes, maybe hurt your eyes. Ocean water is actually around 3.5% salt. So even though it tastes like it's really salty and it seems like it really is, really not that salty, 3.5% salt. The measure of how much salt is in water is called salinity. So when you hear me talk about if water has a high salinity, that means it's going to have a higher percentage of salt. A lower salinity, it's going to have a less percent of salt. So salinity, the measure of the dissolved salts in water. Now, most of the salt in ocean water is sodium chloride. The salt called sodium chloride, its chemical formula is NaCl. So capital N, lowercase a, capital C, lowercase l, sodium chloride. It is actually, if you're talking to a geologist, they're not going to call it salt. A chemist is going to call it salt or sodium chloride, but a geologist is going to call it halite, the mineral halite. Really kind of a really cool compound. It is literally the exact same compound that if you like to put salt on your food at home, that is what you are putting on your food at home. You are putting sodium chloride on your food. That's what comes out of the salt shaker. There are some other salts available to put on food if you have heart problems, because you want to avoid sodium if you have heart issues. So there's other types of salts that we can put on there, but sodium chloride is the one that is most often found in the ocean, like I said, also known as the mineral halite. So where does this salt come from? The salt in the oceans come from minerals from the ocean floor. So if you look at the picture here, imagine rocks in the bottom of the ocean floor and that water is sitting near those rocks. It's going to take the salts that are inside those rocks and evaporate them into the water. It's going to come from volcanoes. So we actually have, when volcanoes erupt on Earth, once again, kind of a weird concept to us living where we do, but it happens all the time. When volcanoes release gases into the air, there's actually salts in those gases as well that can eventually settle into the ocean. Finally, rivers that almost all eventually make their way to the ocean. As those rivers move across land, move across rocks, they're also going to pick up minerals or salts in the soil or from those rocks and then carry it off to the ocean. So that is where the salt actually comes from. So those three different locations is why we have that 3.5% salt found in the ocean. When we look at Earth, we have 5 major oceans on Earth. They can get smaller. We can talk about, if we were in geography class, we'd be getting in more detail with things. But for us here, we have 5. So we have the Arctic Ocean. So you can see that up way northern part. So that's going to be up near the North Pole or 90 degrees north. And then we have the Pacific Ocean, which is going to be on the west coast of the United States, working its way all the way over to where we see Russia and Asia. Then we have the Atlantic Ocean, which is on the east coast of the United States, the Indian Ocean, which is just south of India, but also, as you can see, east of Africa and west of Australia. And then finally, near 90 degrees south, we have what is called the Southern Ocean. So those are the 5 major oceans that we have on Earth. So Earth's 5 oceans. The oceans are really important to Earth. There's 5 major reasons why that your book talks about. The first one, it's a really important source of water for the water cycle. We just got done talking about the water cycle and how important it is for moving water on Earth, taking water and moving it to other locations, giving plants water, giving animals water. It's what drives weather. So the oceans are an important source of water for the water cycle. The oceans also help to maintain Earth's heat balance. So they do a great job at spreading energy and heat from the hot equator to the cold poles. So moving temperature. So imagine it's like, Earth's furnace or Earth's air conditioner moving those temperatures. It also makes it so that our climate is not really too hot or really too cold. So when we look at a planet like Mercury that gets really extreme temperature shifts, so really, really hot to really, really cold, we don't have that. Yes, we have some places on Earth that are cooler and some places that are warmer, but for the most part, when you look at that temperature range, it's not that big, and that's all because of the oceans. Something we don't often also think about is the oceans actually produce most of the oxygen in the atmosphere. So when you're breathing in oxygen, most of that actually comes from the ocean. Inside the ocean, we have these really tiny single-celled organisms called phytoplankton that produce oxygen. And if they were not in the oceans, they were not there, we would not have oxygen. So here's just another picture showing us just how the oceans help to regulate temperature. So moving hot things, moving cool things on Earth. The oceans also help to regulate Earth's temperature specifically, and it has a lot to do with how we talked about the specific heat of water. Remember, water has a really high specific heat. So it's going to take a really long time to warm up. It's going to take a really long time to cool off. It hangs on to its heat really, really well. And then finally, food as a source of food. So even us for here where we live, we can actually get products from the ocean to eat. Costs us a little bit more money, maybe not as fresh. But if you're in a culture that lives near the ocean, most cultures that live near the ocean have really high seafood diets. And you can see why that is, because it's what is available to them in that area, which, by the way, it's a really healthy diet for you to have. There's a lot of healthy things inside of seafood for human beings. Now, the coastal climates, because of oceans, are actually more mild than those that are inland. So because water has that high specific heat and it's not going to cool off and it's not going to heat up really quickly, it hangs on to that temperature. If you're in an area that is near an ocean, your climate is more mild. So if we were to compare Seattle, which is out on the west coast, and we look at Lincoln, Nebraska, which is in the middle part of the United States, Seattle's climate is going to be more mild than Lincoln because it's near the ocean. So even though it's more north, if you look at the temperature there, the average temperature in January, it's only 2 degrees Celsius. Where in Lincoln, it's minus 11. It's inland. Remember that land heats up, cools off really, really quickly. So the temperature swings are going to be much greater in the middle part of the country. So you have two different types of currents that are in the ocean. The first one here are what are called surface ocean currents. So all of those global wind patterns that we talked about that push wind on Earth's surface also push wind on the ocean. And when they push the wind on the ocean, they cause currents on the surface of the ocean. So surface ocean currents, that's fun to say quite a few times in a row, are wind-driven currents that move at the ocean surfaces, and they move for really long distances. Some really famous ones that you may be familiar with is look at the Gulf Stream over on the east coast of the United States. That's a really famous current. It moves really large amounts of water, just like all the other surface ocean currents. It also takes heat from the equator and then it moves it up in the United States there, and we talked about the other day how that will actually bring warm temperatures to a country like Iceland. Another famous surface ocean current is the East Australian Current, the EAC, if you ever watch Finding Nemo, when they turtles hitch a ride on that. So surface ocean currents are really important in moving water and also moving heat on Earth's surface. Now you should have noticed on the last map that you'll get kind of a pattern there with some of, let me click back here, with a pattern in some of those locations. So you'll notice like in the Atlantic Ocean, we see a pattern happening there where it's kind of like creates a circle. The same thing happens in the Pacific Ocean. And you'll also notice if you kind of put your hands up and then rotate them in that direction, if we're in the northern hemisphere, you'll notice they're rotating clockwise. Whereas if I now go to the southern hemisphere, if I look by Africa and South America, I got the same thing going, but look at it. Opposite, same thing, opposite. And why is that? All because of that Coriolis effect that we talked about. So these areas are called gyres. They are large rotating ocean current systems. And they are created because of the Coriolis effect. So remember, that's because we're spinning. and because the shape of the continents. So when the water hits it, it essentially sort of bounces off. So those two things create these gyres in the ocean. And as we just said, in the northern hemisphere, they're going to move clockwise, and in the southern hemisphere, they're going to move opposite of that, or counterclockwise. So here's the one that is created in the Atlantic Ocean. It's called the North Atlantic Gyre. You can see we have the Gulf Stream, the North Atlantic Drift, the Canary, and the North Equatorial Currents, those all create this gyre. Really, also, if you were in a sailboat, what could happen? I could just take a ride and take a ride and take a ride and take a ride and continue to take a ride on that because it would be pushing you along, essentially. Now, in the Pacific Ocean, we also have a gyre, and as you can see here on the west part, this is what happens. So because you have these currents that are constantly circling, if something, like I said, is stuck in it, it's not going to get out. And unfortunately, we as human beings put garbage into water, and this is what has been created in the Pacific Ocean. It is called the Great Pacific Garbage Patch, and there's two of them on either side of that gyre. So if you look on the right-hand side there, you can see there's actually a guy who's kind of swimming through it there. That is all garbage. That is all garbage. Think about what damage this can cause. So not only think of now having species like dolphins and turtles and other things and whales, how are you going to get through that? Now the other problem that exists is plastics do not naturally break down into substances that are going to be absorbed by nature, if you want to think of it that way. They create, if you look at the lower right-hand picture there, what's called a microplastic. Those plastics just keep breaking down into smaller particles until they're ingested by animals, which can kill them. But if an animal ingests it, so let's say a fish eats it, and then you eat the fish, now you've ingested those plastics as well. Once again, not good for us as human beings to consume them as well. So that's why there's a lot of concern over the garbage in the Pacific Ocean, trying to get it out of there just to reduce the plastics, but there is a lot in there. So those are surface ocean currents, and then our other ocean currents are called deep ocean currents. Just like their name implies, these are deep within the ocean. They move much slower than the surface ocean currents. They're taking hundreds of thousands of years to move on Earth. And they are not driven by wind like surface ocean currents are. They're driven by temperature and salinity differences. So think about the things that we've learned about with temperature. We know things that are warmer are less dense and they rise up, right? So warmer currents are going to be less dense and they're going to rise up, just like you see in the picture there. Cooler currents, more dense, they're going to sink. So that thing we've already talked about this here. Now think about salinity differences. When you take water and you put salt into it, you're making it more dense. You're adding more molecules to it. So water that's more saline will actually sink because it's more dense. So cooler, saltier water will sink because it's more dense. This happens near the equator, because what's happening near the equator? You have all of this water that's evaporating there from these warm temperatures. So more water evaporates near the equator because of those warmer temperatures. So the water is actually more saline and more dense there at the equator. Eventually, as those currents move, and as they move near the poles, they're going to change in temperature, they're going to change in density, and they're going to create what's called an upwelling, and you're going to actually see that water come back up. In this particular picture, we see what's called a waterfall, where it's sinking, and it's literally like an underwater waterfall. Now, the great thing about these deep ocean currents, sinking and rising and sinking and rising, is they allow nutrients to mix in the ocean. All of that food that we talked about or we saw earlier needs nutrients. So we need those nutrients to mix to create food for those organisms. So the ocean is very important for us on Earth here. It drives the water cycle, it maintains our heat temperature, it gives us oxygen, and it also provides food for us. It's a very important resource for us. Really, when you think about how much area it's covered the Earth, we haven't even seen half of what's inside of the ocean just because of how deep and how large it is, which we'll be talking about in the next couple of sections.